Audio Jungle. Audio Jungle.
Welcome back to WCSJ. I'm Will H. Smith.
And I'm Will J. Smith.
This just in, there's been a groundbreaking discovery in the realm of virus inhibition. Could you tell us a little bit more about what's going on here, Will?
Certainly. A paper was published by Shahar Keenan and David Abnier on HIV inhibition. Human immunodeficiency virus, also known as HIV, is a sexually transmitted infection. It can also be spread through contact with infected blood or from mother to child during pregnancy, childbirth, or breastfeeding. Acquired immunodeficiency syndrome, also known as AIDS, is a chronic and potentially terminal condition caused by HIV. Now, not everyone who has HIV will develop AIDS, but without antiretroviral treatment, the viral infection will progress to AIDS in about 10 to 15 years. Presently, there is no cure for HIV or AIDS, but there are medications that can slow the progression of the disease. It is estimated that 36.9 million people globally are infected with HIV. This research explores chemical symmetry and how that affects the virus.
Chemical symmetry, what is that?
Let's go to our resident chemist, Dr. Will R. Smith, and let her explain.
Please, call me Will. So, symmetry is a way to describe molecules that allows for the prediction of infrared spectra, electronic spectra, optical activity, orbitals used in the bonding between atoms within the molecule, and other physical properties. More simply, symmetry allows chemists to understand how molecules are constructed and how they act based on matrix algebra. A symmetry operation is a way a molecule can be reoriented to appear to be in the same position as it was before the movement. An example of a symmetry operation is a C2 rotation. As you can see in this video of hydrogen peroxide, when the molecules rotate at 180 degrees around an axis, it appears to be the same as it was before the movement. The C2 symmetry group contains only the C2 rotation operation as shown. Each molecule is assigned a symmetry based on what symmetry operations it possesses, even if the molecule doesn't have symmetry. The research done in this paper is based on the extrapolation of these molecular symmetry principles to whole proteins.
Wow, that's some cool stuff, Will. Thanks for coming on. Here with us now is a colleague of one of the writers of this paper, Dr. Will D. Smith. How are you, Dr. Smith?
I'm doing well, Will. Thank you. And please, call me Will.
I will. So, Will, what can you tell us about HIV and what you're researching?
I worked with David Abnier on this research about HIV. The HIV virion, a non-infectious immature form of the virus that exists outside of a host cell, must undergo a symmetry-dependent transformation to become the dangerous, infective, mature HIV virus. This transformation is mediated by an HIV protease. A protease is a molecule that breaks down proteins, so in order for an individual to acquire the infectious HIV virus, this protease must interact with the HIV virion in a symmetry-dependent manner. As a result, inhibiting this protease function is a research target for drug development.
And exactly what are you researching?
The goal of this research was to determine how to most effectively inhibit the protease based on symmetry principles, stopping the maturation of the HIV virus. In order to better understand the data obtained, first let me explain Gibbs free energy. Gibbs free energy is a thermodynamic quantity describing the maximum amount of reversible work that can be performed by a thermodynamic system under constant pressure and temperature. In other words, the change in this quantity, referred to as delta G, describes how much energy is released or required for a certain reaction to take place. The more negative this delta G value is, the more favorable and spontaneous the reaction becomes. The closer to zero this number is, the less favorable the reaction becomes. This graph, shown here, illustrates this relationship between change in symmetry and the change in Gibbs free energy. As the change in symmetry becomes more drastic, the favorability of the inhibitor binding decreases, which is represented by the increasing delta G value on the graph. When the symmetry change is minimal, the binding to the HIV protease is most favorable. Their data reveals that an ideal substrate-enzyme pair is one in which neither substrate nor enzyme undergo significant change in symmetry upon binding. More energetically favorable interactions are ones in which the enzyme does not invest much free energy in distorting the molecule. So Dr. Keenan and Dr. Abnier are continuing to look for molecules that bind more favorably to the HIV protease than the HIV virion.
Well, that certainly is some great work you're doing, Will. Thank you for speaking with us today.
Thank you, Will.
Wow, I did not know how important symmetry is to our bodily functions.
Not only important, but life-saving.
Up next, a semi-truck carrying Christmas trees crashed on I-95.
You could say it's a symmetry accident.